So now let's take a look at some options for doing feeder automation for implementing it. And just listing a few things right here. First of all, if we don't have communications, we would have to install it. And so we may be adding SCADA communications devices to feeder level, say like the reclosers or maybe some of the switches with automation. The other thing would be we could also use advanced metering infrastructure or AMI for doing some of this as well. The other thing we could add to the circuit, which is pretty reasonable as far as cost, are fault current indicators. And so I'll talk in a little bit what these devices do, but they're pretty effective as far as narrowing down the fault location, although they don't provide any switch automation per se. The other would be, we could just go ahead and add dumb reclosers and sectionalizing devices. We could, as I mentioned before, make sure all our reclosers have communications or radios. We could install some automated switches or motor control switches. And then for our logic, we'd have to implement logic as well. So let me just kind of talk through some of these items right here. So fault current indicator, this device has been around a long time, but it was always a more of a manual operated device where it sensed the fault current, and a little flag would pop up if it sensed the fault current. So the crews would actually have to go to these locations and look at the flag and see if the flag was activated or not. These still have a visual indication on them, but now they have things like flashing LED lights that light up at night, make them easier to see. And then some of these devices also have like radio communications associated with them. And so not only can these devices be used to detect a large current associated with the fault, but they could also give you like measurements of, you know, what the line current is at, say, a given point in the day. So it could have some dual functionality. When the fault's gone, you know, once the fault's been cleared up and the circuit has voltage again, then these devices would actually reset themselves. You need to have that because you might have fault current indicators out there that never get reset. And so they actually have some ability with timers to reset themselves. You got more sophisticated devices that can be installed as well. These devices would install with the hot sticks. There's like a stick the line crews use to put these devices on the overhead. But you also have like more sophisticated devices like this, what they call this lighthouse device, that gets its power through induction off the line it clamps onto. And then it would have more advanced functionality like the ability of capturing like waveforms. And so you got a variety of these different types of fault current indicators or line sensors that you could actually put up on your circuit. Now, Schweitzer Engineering Labs has recently come up with an offering where instead of just having the fault current indicator, they have this married to a receiver which you could place locally. And so you would have these devices you can clamp on, and you could set these up for different current pickup levels. And when the current exceeds a certain threshold, then these devices will activate and they'll communicate to a box via wireless radio, 900 megahertz radio. And this box then can be interconnected into a relay or some sort of a substation automation device. And so this communications takes place through a proprietary protocol. So you have to kind of use all Schweitzer equipment. But basically, it can get an indication from the field in 6 milliseconds. And so this would be the time associated with, say, like a cycle or so. And what's kind of interesting about this is if you were monitoring these lateral points downstream and you're bringing this information up to, say, like a recloser controller, then what you could do is you could use this for some like selective tripping. And so maybe on, if this recloser saw the fault, maybe on some laterals, it would delay tripping, and some laterals it would trip right away. So you can actually have some interesting options with something like this. So, as far as the business case for fault current indicators, a good place of putting these fault current indicators would be on near switch locations. Another good place would be to put these on laterals where you would have, like say, taps off the main feeder. And then what this does is it just enables you to detect the fault faster. It enables you to be more selective as far as where to send the crew. It would actually speed up the patrol and diagnostic time because you can actually narrow down the section of the circuit where these faults are at. And so if you're going to look at a business case for this, and if you had a base case with no fault current indicator, you were going to get these numbers, these timing numbers, which would lead to a certain time taking to restore the fault. Well, if you could drop some of these key numbers down as far as timings, and you could maybe go, as shown in this example, from from an outage corresponding to 1 hour to maybe like an outage corresponding to 0.67 hours. So it may not seem like that much of an improvement to go from 1 to 0.67, but it doesn't really cost that much. I mean, it would cost maybe like thousands of dollars to install something like this, as opposed to spending much more money on an automated switch. And so this is something that some utilities look at in a lot of detail, is putting these types of devices out there, these types of sensors. They don't switch, but they can reduce a lot of these key times. Okay, so what's something else you can do? Well, another way of getting the fault location is to compute that numerically. And the idea would be, let's suppose I had a relay or a recloser up here, and it was measuring voltage and current. And let's suppose you have the model parameters for the line sections underneath it. So you're monitoring the, say like the primary backbone of a feeder, and you have the impedance per unit length. Then if you have the three-phase voltages and currents, what you can do is you can set up a set of equations where you relate the voltage at point A to the distance through these impedances. And so if you have all these currents together, and the fault current is a summation of IA plus IB plus IC, what you actually have in this case is you have two equations and two unknowns. The unknown in this case is D in the fault resistance. Now, you may look at this and it may not look like one equation and two equations and two unknowns, but keep in mind that this is a complex equation, and the quantities you're trying to solve for are real numbers. And so you can actually break this into real and imaginary parts, and then that would actually give you two equations and two unknowns you can solve for D and RF. So this is an impedance-based fault location algorithm. A lot of relays have this built in. You can take the measurements and send this to an outage management system. The outage management system can do the calculation. But this is something quite a few utilities are using nowadays. Maybe they only use this on their primary backbone, but it gives them a way of getting the distance to the fault without having to have a lot of fault current indicators out there. So what you need to do in order to get to this point is you need to be able to take that waveform and process the information. And so if you had this as the current you were monitoring, then you need to convert that to a phasor value. You need to get the magnitude, you need to get the angle. And you can see that at this time that the waveforms kind of converged, that it kind of looks kind of like a sinusoid where you can get the magnitude and angle. But also, if you had a fault event that's short, this would be kind of hard to do. So here shows a case of a fault event, which is not even a full cycle, where you probably had a fast fuse blow in this case. So the question would be, well, what is the RMS current of this waveform? Well, it's not very well defined. There was probably a variable resistance and a switching transient associated with this. And so Where in the top waveform, you could use the RMS value of the voltage and current to do the fault location. That would actually be kind of hard to do with the waveform on the bottom. And so anyway, we can have some success with this type of fault location, but it's not 100% for all the different cases. The other thing about fault location is, suppose you're monitoring the circuit from the top through like a relay or some other sort of data acquisition device. When you're using fault impedance methods, you're basically trying to find an electrical distance that would give you this particular current for a fault. And the problem you run into is if you're tracing from the substation, there's actually multiple locations on the circuit that fault would have occurred that would give you that same level of current. There's not a unique solution to this. The other thing you run into is there's always uncertainty in your data parameters. And so you would actually be calculating a faulted area as opposed to just a specific location, because you can have some margin of error in your measurements in your system model. But this is the thing you run into with a real system here as well, is that you have the multiple locations for where these faults would be at. So you could tell the field crew, I think it's going to be here, 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 and here, and they can try the different locations out. Or what you may have to do is have some other sensors out here to kind of help narrow down some of the possibilities. And so I say a lot of utilities are using some sort of fault location, but they realize it has limitations, given the fact you could have multiple locations corresponding to the same set of measurements. So another thing we could make use of is we could take our manual switches and we can replace them all with automated switches. And so if I had in the substation, the older electromechanical relay still, and some utilities do, I could convert these to microprocessor-based. These could be SCADA controlled, or I could have some local logic opening and closing the circuit breakers tied into these relays. I could have downstream reclosers, reclosers with communications now. I could have automated switches that break load current. They don't break fault current, but they could be used to reconfigure the circuit. And what we would need to have with this is we would need to have a field area network that communicates to all these devices. And we would need to have some place for hosting the reconfiguration logic. And these are all very expensive types of devices here. These are devices that are costing tens of thousands of dollars. And so we're always going to be very, very careful about putting these automated switches in the field. We're only going to use those in situations where the improvement in reliability that we get and the cost or the savings, I guess, associated with that for our customers is going to be basically exceeding what it costs to install the equipment. So we talk about relays. These are microprocessor-based devices we want to be installing. These devices are going to have advanced communications in them. We could talk to SCADA systems, usually through what's called DNP3 protocol. These devices can produce a lot of event information. Not only can they tell you what type of fault would occur, but they can also run fault location. They give you the fault location distance. They give you a lot of different sort of reports as well. But primarily what we want to get off these devices is the fact that a fault occurred. It was such and such a type involving such and such a phase. It has a certain current magnitude associated with it. And even if it wasn't running the fault location algorithm, we know if we had a high current, the fault must be close to the substation. If it was a lower current, the fault would be further away. Something else these devices also have, which is useful in certain automation applications, is the ability of speaking from one device to the next. This is sometimes referred to as peer-to-peer communications, and there's a protocol called IEC 61850, which enables you to talk between these different devices, use what's called goose communications. And so this basically allows you to exchange voltage, current, switch status information between adjacent devices. And so they had this 61850 interface, like these two relays from different vendors could talk to each other. Reclosers we talked about before, these are devices kind of similar to breakers in a way, but they're designed to operate on a single pole basis, and they're designed to be mounted on the top of a pole. And so you have the 3 vacuum switches that are encapsulated in this insulation material. You have a switching mechanism, it's usually electromechanical switching in this high voltage cabinet. And this is going to be tied to a relay that's going to be mounted at the base of the pole. And so this is obviously used to clear faults, but it could also have logic in here for doing auto restoration. This device here can also operate as a sectionalizer, and what a sectionalizer does is it works in conjunction with the recloser. So if I had a sectionalizer, what a sectionalizer would do is, let's suppose I had a fault here. The recloser operates open, and then the sectionalizer would detect the fact that there's no power, and it would assume that the upstream device is operating. And what it would do is it would open up such that when the recloser closes back in, then they could still have service to these customers, and the sectionalizer would be open, and it would disconnect the fault from the rest of the circuit. So a sectionalizer cannot break a fault current. It's not like a circuit breaker, but it's a mechanism that we use if we want to have a way of isolating the fault upstream without having a protection device. And so what's interesting about these is you can put multiple sectionalizers in series. And so what would happen if the fault were, say, like right here, the recloser would operate the first time and this device would turn off. Recloser operates the second time and this device would turn off. And then the third time we closed in, then what would happen is we would still see the fault, and then this device would turn off, right? So it's a little bit of a manual process we have. We don't have communications between the reclosers and the sectionalizers, but it gives us an opportunity to clear the fault with having a cheaper type of a switch. You can use a recloser as a sectionalizer. I mean, it'd be a kind of expensive sectionalizer, but reclosers could be set up in a sectionalizing mode as well. That's why some utilities, instead of buying standalone sectionalizers, may decide just to use reclosers in there. And one nice thing about using sectionalizers is sometimes you have problem coordinating 2 or more reclosers in series. And so if you have problems with coordination, this is where sectionalizing gets used, or sectionalizing modes get used, because you don't have to have protection coordination. The same recloser keeps operating, but you can sequence the operation of the sectionalizers in order to isolate the fault still. Remote controlled switches are just basically manual switches that have a motor actuator. And so you could actually operate this switch manually with a hot stick, but if you have a motor on here, then what you do is you have a local switch controller, and you basically use this local motor to open and close the switch. This would be a lot less expensive than using a recloser in the field. It could break a load current, but it would not be able to break a fault current. And so you'll see these remote controlled switches out there as well. So in order to tie things together, we need to have a communications infrastructure. This again is referred to as a field area network. And we would talk to all these different reclosers and switches out in the field in order to open and close when needed in order to restore customers a service. You could have a radio system for this. You can have cellular communications for this. And then the radios would go back to towers, and the towers would be tied into like a fiber network or microwave network. This is the utility wide area network. And then at some point, the utility network is also tied into different sort of applications like outage management or SCADA, let's say. So for the logic, we have lots of different options for coming up with the switching logic. Probably the one that's most common right now is just have a centralized system, to have everything tied into SCADA and either have an operator manually operate the switches or have some central logic for that. We could put this logic in substations. Some utilities do that, or we can have a totally decentralized approach where all your logic is in your relays in the field. So in the centralized approach, you basically kind of have a single master and you have all these different outstation devices. Again, you could have an operator just do all this stuff in terms of minutes when an outage has occurred, or you can actually have some logic running in the distribution management system that automates the switching operations. And so again, all you need to do is need to get this circuit reconfigured like within 5 minutes in order to avoid a SAIDI operation. And so this would be what a lot of utilities would do, is they would just kind of do all this stuff centrally from a centralized master logic. You can also put the switching logic in substations, and you would just have a number of substation computers, and these substation computers are all talking with each other. And so the substation computer would keep tabs on like how much loads on its transformers and what each feeder is doing. And then if you need to do reconfiguration, then the substation computers would talk to each other, exchange information, and then work together to figure out how to reconfigure the circuit. And then finally, you have what's called distributed logic, where if you had an IED associated with each switch in the field, they would just simply talk with each other. They would inform the SCADA system what's going on, but all the logic would actually be done at the feeder level. You may not even have to have the substation involved. You just simply have these devices talking with each other. And so this is sometimes referred to as peer-to-peer. We might call this like P2P, but this would be for a distributed approach. So if we're doing feeder automation on a circuit, as I mentioned before, a lot of this is based on the assumption that we have loops. You'd have a source 1, you'd have a source 2. You can have a number of different switches in series. I'm just showing a 5-switch loop system right here, but you could have 7 switches or more switches than that if you want to. But basically what you need to do is you need to have a mechanism once a fault's occurred, again, for figuring out, well, what switches have to open and close in order to restore as many customers of service as possible. So as an example of central logic, let's suppose a fault occurred here. A fault occurred here, and let's suppose these are switches. B, C, and D are switches, they're not reclosers, are not breakers. Well, what would happen if you had the fault here, then the nearest upstream protection device would operate, and that would be the circuit breaker at A. So it actually goes from red being closed to green being open. Then everybody on the circuit right here would be out, right? C is the tie switch in this case. And so you can actually restore service to these guys between sections A and B. And so what happens is that you have a central master that would be notified that the circuit breaker tripped open. So they know that the circuit's dead right. What they could also do is either they get an event record, they ping switch B, and they want to know if switch B saw the fault, right? And so if you had a situation where switch B saw the fault, then what you would do then is you would open switch B and you would close A, and any customer between A and B, you could restore the service while you're waiting for that section B to C to be repaired. And so all that information is going to a central point. All the commands are coming from that same central point in this case. And so this would be a centralized type of scheme. Many utilities would use something like this. Now, the thing about this sort of scheme, if I had a hospital here and critical load, then you would want to be able to restore that hospital as fast as you can. And to have this centralized system get all this point information, make a decision, and send commands back out to the field, that's going to take quite a bit of time. That hospital would probably want to be restored in cycles, not in seconds. And so how do you speed something like this up? Well, what you would do is you would run peer-to-peer logic, that each of these devices would have its own IED, and these devices would have the ability of talking to each other, maybe over a fiber network or a fast radio system. And so all the decisions are made in the field, and because of this, this can operate extremely fast. And so let's suppose I have a fault here between A and B, and what I've got is I've got a critical customer, say like right here. All right, so what's going to happen is this circuit breaker A, it's going to trip open. So anyway, what we need to do is we need to isolate the fault, right? And so in order to isolate the fault, then what I need to do is I need to open the switch. Basically, what's going to happen is switch A, its IED is going to contact the IED for switch B and basically say, hey, you know, I had to trip on overcurrent. If you didn't see the fault, that means the fault must be between A and B. Then what B can deduce then is, okay, if the fault's on here, I can go ahead and open up to isolate the fault. And so it's the communications or the interaction between the IEDs for A and B that eventually cause B to open up. Now, the next thing that would occur is that B knows there's so much load current on it. That IED knows that so much load was going through this B node. And so what it's going to do, it's going to send a request to switch C, and its request is going to be something like, hey, you know, I had about 100 amps of current. If you can pick up 100 amps of current from source 2, why don't you go ahead and switch closed, all right? So then based on the communication between B and C, then what's going to happen is C decides it could pick up the load and C is going to close in. And so the same decision making can be taking place locally by having these switches communicate with each other. Where this gets more complex is we have like 3 sources. If you get 3 sources, this logic is very complicated for peer-to-peer. But if we had a simple loop, then this is usually a doable process. So here's an example of an old style scheme that we used to do with reclosers. And this didn't involve any communications and any real intelligence in the field. Basically what we would do for those 5 switches, we may just put reclosers everywhere. And what we would do for this tie switch is we would have a voltage measurement on either side. So the tie switch would know if one of these 2 feeder sections lost power or not. So let's suppose we had a fault right here in F2. What would happen? Well, what would happen is this is the normal direction of flow, right? Fault happens at this point F2. What happens is this recloser senses the fault and operates open. Then what happens is this tie switch observes there's no voltage here, and it goes ahead and closes in order to be able to help transfer load over to this bottom circuit. Well, the problem is this fault's still here. And so once this tie switch recloser closes in, now C is going to see the fault. And what's going to happen is it's going to lock open. Okay, so this device is going to lock open. This device on the left is already open. And now what we've got, we have a situation where both of these devices upstream and downstream are open, and the customers that were over here now are going to be restored to service. The problem with this scheme is it doesn't involve any communications or logic, but we had to put 2 faults on the circuit in order to get us to this point, which a lot of utilities aren't really that comfortable with. And so this is an older style scheme that could have been used without communications. And this assumes that you got these reclosers all over the place as well. So a more sophisticated approach would be to have a loop scheme that uses peer-to-peer communications. And we've got these recloser controllers, and they're all talking with each other using this goose messaging from 16850. So let's suppose we had a fault here now. Well, how's this scheme going to work? Well, basically what's going to happen again is this recloser B is going to see the fault. So it's going to go ahead and it's going to lock open. And this device sees that there's no voltage, and so it wants to close in. But what's going to happen now is there's going to be a discussion now between B, C, and this particular tie switch T, where basically then C's going to know, hey, you know, B saw the fault, I didn't see the fault. So that means that C, instead of just closing into the fault again and then locking open, can just open up, all right? So basically, based on this negotiation right here, C can go ahead and open up to isolate the fault. And then it could talk to tie switch T and says, hey, I just opened up. I've got some load here I'd like you to pick up. If you can pick up this load, please close in. And T can oblige it if it has the capacity, and it can close that switch in. There could also be communications between T, D, and A, because you want to find out whether you have enough capacity to serve that load. And the only way you're going to know that, and you could even talk to the substation, the only way you're going to know that is talk to the switches on the adjacent circuit and just make sure they're not overloaded. So this is what's referred to as a peer-to-peer based scheme. And if you want to have very, very fast operation in the field, say on order of cycles, this is what you would actually use then, instead of going to a master centralized type of a scheme. But this is what's enabled by having the faster peer-to-peer protocols that are available in protocols like 16850. So anyway, it's an expensive scheme, but it can work very, very quickly for critical loads. So next thing we're going to do is we're going to look at cost benefit analysis, because just because we can do it just doesn't mean we can. You know, having these automated switches in the field for responding to these types of events, it's sort of like you spend like $20,000 on a car just so in case of emergency you'd be able to drive to the hospital, right? And how often would this emergency occur? Maybe it occurs like once every 5 years. Once every 5 years, you'd have to drive the car to the hospital. So you're spending $20,000 for a car that's just sitting there for basically 5 years. In that period of 5 years, you need to make sure that that car is going to be able to go with the turn of the switch, right? So if you go out there in year 3 at 3 o'clock in the morning and the car doesn't go because it's got a dead battery, that'd be a waste of your investment, right? And it's the same thing with doing feeder automation. If you're spending all this money, you're basically spending money on a system that's got to operate like on a cycle by cycle basis perfectly for like 5 years. So when the time comes, it performs as needed. And that's a pretty tough thing operationally, you know, to have something out in the field on a utility system. And, you know, in its second or third year of operation, it's just basically sitting there doing nothing. And all of a sudden, everything's got to kick in and work perfectly. But anyway, in the next video segment, we'll do some business case analysis, and we'll see kind of like how decisions would actually be made in terms of whether to make these types of investments or not.